When we began our investigation of eigenvectors and eigenvalues, we started with an example of a matrix that we saw was similar to a diagonal matrix. Now that we've developed some more machinery, we are ready to tackle the question of when a matrix can be represented as similar to a diagonal matrix. To start out, let's assume that A is an n by n matrix and that there is a basis for Rn, which we'll call B, consisting of vectors v1 through vn that are each eigenvectors of A with associated eigenvalues lambda I for each I between 1 and n. Given any vector x in Rn, there's a unique way to express x as a linear combination of these basis elements. As we've seen, this makes it handy for acting on x by the matrix A. Namely, if we take the product ax, then we can use linearity and the fact that each of these vectors is an eigenvector for A to see that ax is c1 lambda 1 v1 plus c2 lambda 2 v2 plus etc. plus cn lambda n vn. So that is to say, A takes in as input any linear combination of the basis elements and also outputs a linear combination of those basis elements in a very predictable way. Since everything in sight is a linear combination of the basis elements, we can make this expression much more pleasing by changing from the standard basis with basis vectors e1, e2 down to en to our new basis b. That is, we can write ax in coordinates corresponding to our new basis as the vector c1 lambda 1, c2 lambda 2 down to cn lambda n. And we can think about this as the result of a diagonal matrix with the lambdas down the diagonal, multiplying the vector with entries c1, c2 down to cn. And of course, we can recognize this vector as the representation of x in this new coordinate system. So if we label our diagonal matrix D, this is the diagonal matrix D times x expressed in the coordinates for B. So as we've seen previously, as long as we're willing to change our coordinates, we can think about the action of such a matrix geometrically as being like the action of a diagonal matrix. So in each of the coordinate directions, it's scaling by lambda I. Now, while this is conceptually pleasing, it is practically unwieldy. Our intuition for space is tightly linked to the standard coordinate system. So it is customary for us to express this relationship in terms of the standard coordinate system. And we can do this using the change of basis matrix, P, whose columns are the basis elements, and its inverse. We can recognize that AX is the result of taking AX written in the coordinates for B and multiplying it by the matrix P. Now, using the top line, we can rewrite this as P times D multiplied by X expressed in the coordinates for B. We can use the associativity of matrix multiplication to shift this set of parentheses over to the P and the D, and we can remember that we obtain X in the new coordinates simply by multiplying X by P inverse on the left. Now, we've encountered this sort of relationship before in exercise 3 from the invertibility and bases homework. There, we said that the matrices A and D are similar. This particular instance of similarity is so important that it warrants its own name. We say that the matrix A is diagonalizable if it is similar to a diagonal matrix. Explicitly, this means there exists a diagonal matrix D, an invertible matrix P, and A is equal to P, D, P inverse. As we've seen, if Rn has a basis consisting entirely of eigenvectors of our matrix A, then A is diagonalizable. It turns out that if our matrix A is diagonalizable, then there also exists a basis of eigenvectors of A for Rn. So let's assume A is equal to PDP inverse, where P has columns V1, V2 down to Vn, and D has lambda 1, lambda 2 down to lambda n along the diagonal. We claim that each of V1, V2 down to Vn is an eigenvector for A with eigenvalue lambda I. We note that this is sufficient to show that Rn has a basis of eigenvectors of A, namely P is an invertible matrix. That means that the columns of P span Rn and are linearly independent. Therefore, they are already a basis. We just need to show they are actually eigenvectors. Since A is equal to P, D, P inverse, we're going to compute AVI in steps. The first step is to be able to compute P inverse times VI. Since it's hard to compute P inverse if we don't know exactly what P is, we're going to think about, instead of solving the equation P inverse VI is equal to some vector B, multiply both sides by P. The second equation is much easier to solve. Namely, if we take the basis vector EI and multiply that by P on the left, we will get the ith column, which is simply VI. Multiplying on the left by P inverse, we see that EI is equal to P inverse VI. This tells us that P inverse VI is simply the ith standard basis vector EI. Next, we'll compute D times P inverse VI. Replacing P inverse VI by EI, we can see that D times EI will simply give us the ith column of our matrix D, which is of course the entry that has lambda I in the ith column and the ith row, and zeros everywhere else. That is of course simply lambda times EI. And finally, we can compute A times VI, replacing D P inverse VI by lambda I EI, and using linearity to pull the scalar through the matrix multiplication, we're left with lambda I P times EI. We know that when we multiply a matrix by the ith basis vector, we simply get the ith column of our matrix. But that's simply VI. So we can see here that A multiplied by VI is lambda I VI, where lambda I is the ith entry along the diagonal of our matrix D. So we've now shown that if our matrix is diagonalizable, then Rn has a basis consisting entirely of eigenvectors for our matrix A. This establishes the following characterization. An n by n matrix is diagonalizable if and only if there is a basis B with vectors v1, v2 down to vn for Rn consisting of eigenvectors of this n by n matrix A. Now, we've seen that Rn has a basis of eigenvectors of A if and only if the geometric and algebraic multiplicities of all the eigenvalues of A are the same. So this provides us an important and common special case. If A has n distinct eigenvalues, then A is diagonalizable. And explicitly, A will be similar to the matrix D with entries lambda 1, lambda 2, down to lambda n, the eigenvalues of A along the diagonal. So in our next video, we'll work on diagonalizing several matrices.